Hello, everyone, and welcome to the third in our series of lectures on radio this IAP. I'm Daniel Sheen, station manager for the MIT Radio Society. Before we start, I'd just like to make a few quick announcements. First of all, for any of you interested in getting your amateur radio licenses, we're holding the FCC exams next week over in Building 1, Room 1150, right after the lecture. And then also this weekend, we're participating in the Auroral January VHF competition. If you'd like to join us, you're welcome to. We'll be operating from up on the Green Building. And you don't actually need a license to participate in that because some of those present will have one. And along those lines, also, if we're currently fundraising to preserve that station, if you go to our website, w1mx.mit.edu, you can find more details. It would be great to have all the help that's available with that. So if you enjoy this, if you enjoy watching these lectures, if you think amateur radio clubs are a good thing, please consider donating to that. But with that, I'd like to introduce our speaker, Dr. Jim Labelle. Dr. Labelle is an experimental plasma physicist and a professor of physics and astronomy at Dartmouth College. He has a bachelor's degree from Stanford University in physics and master's and PhD degrees from Cornell, and his postgraduate work at the Max Planck Institute in Garching, Germany, and at the University of Utah in Logan before eventually becoming a professor at Dartmouth. So with that, I'd like you all to give a warm welcome to Dr. Jim Labelle.
All right, well, thanks very much. So I guess what I'd like to do with my, thanks for giving me the opportunity to speak here, and what I'd like to do is talk about strange kind of noises that you can hear, natural noises coming from the sky that you can hear in the radio, that have been known since the early days of radio. And so I thought I'd go over them, and maybe by the end of the talk, some of these graphs on the front will be more familiar to us. Let me just first put a slide up that shows the, whoops. This will advance. This slide not advancing here. There we go. Okay, first I thought I'd show a few just pictures of some of the antennas that my research group deploys around the world. So what we do is we deploy these kind of arrays of these magnetic loop antennas in different locations, generally at high latitudes, underneath the southern lights or the northern lights, picking up natural signals, radio signals coming from the aurora. And so that's what we've been doing, and it's a subset of what I'll be talking about today. But it turns out that to detect these kind of natural signals, you don't need anything so fancy as these kind of somewhat large loops. You can detect them with simply throw a wire out, attach it to an amplifier, and then put the amplifier to a loudspeaker. And what you'll first happen will be terrible oscillations and stuff, and you'll have to tinker around with it a bit. But once you get it stable, you can hear some amazing things. And so here's an example of something that you can hear, if I can get it to and these are called whistlers for obvious reasons. It's a short burst of radio noise. Starts at high frequency and goes down to low frequency. By the way we image our radio signals, you're probably familiar with, but it's called a sonogram. And the idea is that you put the frequency of the radio signal on the vertical axis and time on the horizontal axis. In this case, just about 10 seconds or 15 seconds of time on the horizontal axis. And then dark represents a strong signal at a given time at a given frequency, and light represents a weak signal. So there's a way of sort of imaging the radio signals and how they evolve with time. And on this kind of depiction, a horizontal line is typically a signature of a man-made signal, because humans like to transmit on a particular frequency and receive on that frequency. But other features that are not on a fixed frequency, like these whistlers, are natural in origin. And so these whistlers were observed in the earliest days when they first started. They were discovered in World War I, which was the first time people started putting wires out, okay, and listening, and they heard these things, and they didn't have, of course, any explanation for them. Here's another example. This is an example of what's called a whistler train. These whistlers often happen in trains. Whoops, that's not what we wanted to have happen. We wanted to listen to this. There's your initial one. You hear how subsequent ones are much more stretched out. And this turns out to be a very important clue about the cause of the whistlers. They often occur in trains in this, and when you have these trains, the subsequent ones are much more drawn out than the initial ones as they go along. Yes.
This is in the 110 kilohertz.
Yeah, that's right.
Some of these things can be heard higher hertz.
We'll get to some of those. I'll show you some examples of those.
So you are just really talking about stuff that's in the
Here I'm talking about simple experiments that you can do, as I said, simply taking a wire, amplifying it, and sending it directly to a loudspeaker with no processing. So the signals, the radio signals are actually in the audio frequency band. So you convert the radio to audio and you can hear it with your ear. Let's see, some of the most striking whistlers have been detected by satellites, actually. Let's listen to some of these. This is from the recent Van Allen probe satellites. And they give some quite striking whistles. You get a much more noise-free environment up in space. And so really quite striking sounds. You also have what's called whistler storms. Let me show you one of those. This is an example of a whistler storm, just where they're huge numbers, almost on top of each other. Sometimes you can't even distinguish the individual ones. They're coming so quickly. It's called a whistler storm. So these are natural signals in the audio range. And so the question is, what causes? They were discovered in World War I, as I mentioned, and first described in 1919 scientifically in a scientific paper. But they remained a mystery for nearly 50 years, until the 1950s. And finally, the theory that was put forth, which is a remarkable theory, was put forth by L.R.O. Story, who was a graduate student at the time. So that should make, hearten all of you students out there. So Story put this out. And the key thing about the feature of the theory that's critical for whistlers, in fact, for almost all the natural radio emissions, is the Earth's magnetic field plays a really critical role. As you recall, the Earth's magnetic field is basically like the field of a dipole, okay? And so what I've shown here in this graph right here is just one example magnetic field line. And so the story of whistlers starts out with a lightning stroke, actually, a flash of lightning in one hemisphere or the other. You get a lightning flash from a thunderstorm. And what lightning does is, first of all, it gives, of course, a brilliant optical display. And I think you guys saw a lot of this last week, maybe, in a previous talk. But in addition to the optical, lightning gives off what's called a spheric. It gives an impulse of radio at all frequencies, right? An impulsive radio emission. It's called a spheric. And if you put it on a sonogram, it looks like a vertical line like that, okay? But here's the remarkable thing that happens. That spheric energy couples into the Earth's magnetic field, and it propagates along the field tens of thousands of miles, okay, along the magnetic field out into space to the other hemisphere of the Earth. And along the way, the signal is dispersed. That is, in the charged particle environment, the plasma environment of the Earth, the signal, the high frequencies travel faster than the low frequencies, so that when the signal arrives at the other end of the field line, it's no longer an impulse, but the high frequencies arrive first and the low frequencies. You have yourself a whistler. And what happens is that not only does it make this tens of thousands of kilometer journey to the other hemisphere, where it can be detected, okay, but some of the energy is reflected and goes back to the previous hemisphere, and then gets reflected again and back to the back to the other hemisphere, and so forth and so on. So this is how you get these Whistler trains. You get the initial lightning flash in one hemisphere, propagates to the other hemisphere dispersed, reflects and comes back to the first doubly dispersed, goes back to the other hemisphere triply dispersed, and so forth. And people have observed up to 30 of these trains of Whistlers coming along. A remarkable story. I always found this amazing that this happens. Yes?
Now, are lightning strikes only...
That's a good question. There are other phenomena that could produce spheric-like signals, like, for example, a nuclear explosion. I'll just put that one out there. Produces something called electromagnetic pulse, which is a very similar phenomenon. But I think of the natural signals, I think lightning is the main producer of these impulses. I mean, there may be other kinds of discharges that occur that could produce them. Well, most of them being lightning related. So, for example, there are these other types of lightning that occur called sprites, and they're kind of upward discharges of lightning. These kinds of lightning also produce spheric-like signals. But most of the cases I know are related to lightning. Yes, another question. Well, the world record is something like 30 or 40 of them. It's a couple of seconds, as you can see, per back and forth. And so it might go on for a minute or more before the energy kind of peters out and you stop seeing them. Yes?
So how many times it does?
You can tell a great deal, actually, it turns out, from this dispersion. And so this dispersion tells you what the density is of the electrons out here in outer space. And the time delay also tells you information. So actually the time delay tells you the density of the electrons, and the dispersion tells you which field line it's on, what the field line strength is. And so from those two pieces of information, you can use these things to map out what the density is out in outer space, just from Whistler observations. Just from sitting on the ground receiving these things, you can map out what the density is. This was how the density was mapped out in space before satellites. People were able to map out what the density structure was out in space using Whistlers. It was quite a remarkable achievement. I wanted to mention that, let me go over, I just wanted to play you one more Whistler sound. This kind of shows you the evidence of what you're going to hear here is you're going to hear the click of the spherics, and then you're going to hear the Whistlers. So let's see if I can get this to sound here. So those are the spherics. There's the Whistler. So you hear the click followed by a Whistler. These are called two-hop Whistlers. So the click is a lightning, and you can hear the click because the lightning's local. It's in our hemisphere. And then the Whistler comes delayed because it's gone back and forth to the other hemisphere. It's called a two-hop Whistler. Yes. Yes.
What is the y-axis scale here? Is that kilohertz?
That's kilohertz. Yep, I should have labeled that. I did on the other graph, but didn't on this one. But that's kilohertz. So this is in the audio range. That's why we can hear it. So let's see. I also wanted to put a yes. Yes. Absolutely, absolutely. That's part of the critical Whistler analysis. If you want to use Whistlers to remotely detect the density in outer space, you actually have to make that correlation. You have to figure out which click goes with the Whistler so you can get the time delay, because that's a feature that you need in order to map out the density in outer space. Amplitude, well, what can happen, the amplitude can vary widely in the Whistler, because as it makes that long peregrination, it interacts with electrons, and it can be either amplified or attenuated. And so the amplitude can be kind of all over the map on the Whistler relative to the spheric. So that's a tough one. It does have diagnostic meaning, but it's more difficult to interpret. Pardon me? Well, sometimes you can. Sometimes along the way, Whistlers will trigger other signals, other VLF signals that can be picked up. And so you'll sometimes see whistlers with a triggered signal coming after, and that particularly is true in space. The triggered signals often don't make it down to the ground, but if you observe whistlers in space, you'll see various kinds of triggered signals associated with them. So there is a whole field of literature, believe it or not, hundreds of papers on this subject. Let's see, let me just mention one thing. I want to give a plug for a Dartmouth professor, Millette Morgan, his claim to fame was after graduate student L.R.O. Story put out this theory, there was a huge, it was like the Oklahoma land rush for space scientists. They all piled in wanting to be the first ones to verify this theory. It was considered quite remarkable at the time that this could happen. And the winner of the race was Professor Morgan, our institute. And here's the paper. This is from Nature, 1956. And I think I can quote to you the first paragraph. It says, observations which we have conducted near geomagnetically conjugate points at about 50 degrees geomagnetic latitude in the Aleutian Islands and in New Zealand appear to confirm L.R.O. Story's remarkable theory. And the evidence is over here. What he did with his New Zealand colleague Gordon Alcock, they put receivers at both ends of the magnetic field line. And so at one end, the top one there, they picked up the spheric. And then a little bit later at the other end, they saw a whistler. A little bit later at the first end, the reflected whistler. A little bit later, the three-hop, and so forth. So they were able to get really direct evidence of this theory. It was the first direct evidence, and that's what was one of Millette Morgan's claim to fame. And he's the founder of our research group at Dartmouth that I'm a member of. All of us right now, that group now has 6 or 7 professors, but he was the starting point for that. And this was probably his most famous result. Let me carry on because I want to tell you about some other strange signals that you see out there. Let me play another one for you. So this one right here, this is called chorus. See if you can, actually it's often called dawn chorus specifically. So did you hear all those kind of chirping sounds? So this is another, whistler. It's in the same frequency range as the whistlers, the audio frequency range. Again, just picked up by a wire on the ground connected to a loudspeaker. The radio signals themselves are at the audio frequency band. And this is called dawn chorus. It occurs in the dawn time period. It was called that partly because it resembles like the sound of birds or frogs at dawn, I guess is kind of where people got the name dawn chorus, like birds at dawn. But it actually does occur at dawn, interestingly enough. Let me play you another example of an even weirder one. You can see on the spectrogram, whoops. You can see on the spectrogram that this is kind of going to be a weird one. Pretty strange, natural signals made by nature. By the way, I should point out these were recorded by an amateur, Dave Ewers, and some of the whistlers I showed were also played by an amateur, recorded by amateurs. There's a big amateur community that calls themselves VLFers or loafers, I guess, low frequencies. And let me turn this off. And so there's a big amateur community, and so if you go out on the web, you'll find a lot of recordings of these chorus and things made by amateurs. As with the whistlers, you often get more beautiful results making the records in outer space, which of course an amateur has a hard time doing. But here's from the polar satellite.
May 31st, 1990, chorus.
This is very typical chorus. Rising tones kind of predominate.
The University of Iowa.
Let's see, and here's another weird one. Let me play you another weird one here. These are pretty strange. This is from the Van Allen satellite, one of our recent probes that's actually still up now, taking data. Here's another Van Allen probe's data. Whoops. Let me just play this if I can get this to play really quickly. Again, rising tones predominating here. Sounds almost like droplets in the water or something. And this one they call giraffes in the sky, it's called. Giraffes in space. By the way, this kind of roaring sound below is a different phenomenon. That's called hiss, okay, as distinguished from the chorus, which is the discrete features. So let's see, I could talk a few minutes about what causes the chorus, okay? Chorus is actually quite a complex topic. In fact, it's really just being the details of chorus and actually being able to simulate chorus being generated is fairly recent. It's in the last few years, actually, that people have really got the details down. But the broad picture has been known for a while. So let me tell you the broad picture of what causes the chorus. The interesting thing about it is it's tied in with some very large-scale features of our outer atmosphere and magnetosphere. And in particular, it's tied in with the fundamental circulation cycle of the outer atmosphere, which is driven by the solar wind. So this is a picture here of the Earth and its magnetic field, okay, field of a bar magnet. And the solar wind is a stream of particles that essentially boil off the sun all the time, making a wind blowing out of the sun that brushes against the Earth's atmosphere. And what it essentially does is it sets the outer parts of the Earth's atmosphere into motion away from the sun. Now, it's somewhat complicated because it's not just a frictional process. It turns out the frictional process does happen, but it actually involves what's called magnetic reconnection. The magnetic field plays a major role in this convection cycle. But anyway, the upshot is that the solar wind in blowing past sets the outer regions of the atmosphere, streams them along away from the sun. And then, of course, if that was all that happened, it'd be bad news for us, right? There'd be no atmosphere after a while. So what goes back has to come back. So basically what the solar wind does is it drives a convection cycle. So the outside gets driven this way by the solar wind, and then the stuff returns down the middle, right? Returns down the middle so it can get back to where it started from. And it's just a perpetual cycle. It's called the Dungy cycle, after Jim Dungy, the person who discovered it, first described it. And it's the fundamental and most important kind of circulation pattern of our outer atmosphere, of the magnetosphere. And chorus is involved in this because, this ties into the chorus because let's look at it. What we're looking at here is a side view of the Earth, okay, with the North Pole at the top and the South Pole at the bottom. But let's suppose we look down now on the North Pole, for example. And so you have this return flow coming back towards the Earth that's driven by this circulation, driven by the solar wind. By the way, it's a very uneven, it's not a steady convection. It's very uneven because there are lots of things changing and driving it. But anyway, you get this flow. And remember, all the gas out here in the magnetosphere, it's all charged particle gas. It's all, mostly protons and electrons. No neutrals out there. So you've got a charged particle gas being pushed in, essentially, to where the magnetic field is stronger. So two important things happen. First of all, when it hits the magnetic field here, charged particles get bent by magnetic fields. We all, hopefully many of us know that, okay, right? And electrons get bent one direction, protons get bent the other direction. And the electrons get bent towards the dawn, okay, which is, that's where the chorus is going to happen. Okay, the other thing interesting that happens, besides the electrons being bent one way and the protons being bent the other way, is that as the particles are compressed into higher magnetic field, okay, the particle energy is conserved, okay, but the energy gets distributed differently between the perpendicular motion of the particles, that is the motion of the particles perpendicular to the magnetic field, and the motion of the particles parallel to the magnetic field. And what happens is you start out with particles that are in equilibrium here, that have randomized velocities, comparable velocities perpendicular and parallel to the magnetic field. And when they get pushed into the higher field, what happens is that the perpendicular gains at the expense of the parallel. The energy overall is conserved, but the perpendicular velocity gets much, much larger than the parallel velocity. So you have a very anisotropic electron population in this region. And that is an unstable feature. You know, nature doesn't like that. Nature wants the velocities to be randomized. And so this is an unstable feature, and so nature is looking for some way to get rid of that excess perpendicular energy and make it so the electron velocities are randomized once again. And that turns out to be key to the chorus. That's where the chorus comes in. You might ask, you know, how is it that that the electrons can get rid of that excess perpendicular, you know, energy that they have? Well, here's the idea. First of all, I think we know, let's have a little video here that shows it, but you know, in a magnetic field, the fundamental motion of a charged particle in a magnetic field is that it circles around the magnetic field, right? This is called the gyro frequency, and the frequency of the gyration depends on the strength of the field. The stronger the field, the stronger the gyration frequency. And so this leads to one of the two fundamental resonant processes in the ionosphere, in space physics. And what I'm talking about here is a resonance between the particle motion and, in our case, the radio wave electric field. So it's called cyclotron resonance. So the electrons are making a circle around the magnetic field with a frequency that depends on the strength of the field. It's called the gyro frequency. And you can imagine that if your radio wave electric field happens to be varying, and I have a little kind of, remember the radio wave electric field is going to be switching back and forth, right, twice per cycle of the radio wave frequency. And so the idea is if the radio wave frequency is matched precisely to the cyclotron motion, so that as I've just shown there, so that the radio wave electric field switches when the electron switches direction and switches back like that, then you can have a resonant interaction between the electric field of the radio wave and the electron, right? Because if they're in phase, that means the electric field can constantly be pushing the electron, constantly accelerating it. And when the electron switches direction, if the wave field switches direction at the same time, the wave continues to accelerate the electron. So you can have continuous acceleration of the electron. This is called the cyclotron resonance. And it happens when the radio wave frequency matches this frequency of gyration of the electron. And by the way, I talked about acceleration. It doesn't have to be acceleration. It can be deceleration. In fact, the case I've shown here is deceleration, I think, where the electron is going in the same direction as the field. Of course, the electron is retarded by the field. And so this electron is actually going to be decelerated. And that's the key to how the chorus is formed. The chorus is formed by this cyclotron resonance because this is a way to extract perpendicular energy out of the electrons, right? Because this is the perpendicular motion of the electrons that's making this circle. And if you decelerate the electron, that means you're taking the perpendicular energy away. Now, energy can't be destroyed, okay? So that energy has to go somewhere. The wave grows, right? The radio wave grows in amplitude. It gets the energy that the electrons lose. And so the idea is that in this situation that we have that obtains in this region over here, okay, where you have these very anisotropic electrons, perpendicular energy much greater than parallel energy. On average, statistically, what will happen is that the electrons will tend to get decelerated by the resonance with the wave, and they'll give their energy to the wave will grow. That's in a nutshell, the source of the chorus wave. It grows spontaneously because it gathers up energy from those electrons. And you might ask, well, why does the frequency change in weird ways? Well, that has to do with the dependence of this resonance frequency on the magnetic field. The resonance frequency varies with the magnetic field, and you can see it's minimum. The magnetic field is minimum at the equator. And if you go off the equator, the magnetic field gets a bit bigger. And that's what's going on with the chorus. The electrons, start resonating at the equator with a relatively low frequency radio wave. And as they move off the equator, they resonate with higher and higher frequency waves because they get into higher magnetic field. And this makes a rising tone. The other direction, a falling tone. Tends to be the case that chorus starts near the equator and shifts off, so you tend to get rising tones. We could kind of hear that in the noise. It tended to be rising tones. The process is a bit more complicated than I've described, but this is the basic physics of it. And it's quite interesting, and it explains why the chorus occurs at dawn as it does, and why you get these rising tones. And the other thing that's interesting about the chorus, by the way, is that this region where the chorus happens, right in this region at dawn and a few Earth radii away from the Earth, this is exactly the region where another very significant feature of our environment is, and that is the Van Allen radiation belts are exactly in this region. The Van Allen radiation belts are regions of trapped charged particles that are trapped in our magnetic field. Now, these are not the particles that are causing the chorus. These particles in the Van Allen belts are thousands of times more energetic than the electrons that are causing the chorus. But the chorus has a substantial effect on these. And so chorus turns out to be a significant player in terms of scattering these high energy particles so that they disappear, they're lost. And the chorus can also accelerate them. It contributes both to causing the radiation belts and to losing the radiation belts. And the radiation belts are quite a significant feature of our environment, as well as the Dungy cycle. They're a very significant feature of our local environment. And chorus plays an important role with those. So anyway, shall we move on and talk about the aurora? Okay, so the aurora is where my group has made most of our measurements. And of course, you can go online and find tons of beautiful pictures of aurora like these. The remarkable thing about the aurora is that the structure of the aurora that you're observing there, that is governed by the magnetic field. So many things we've talked about tonight have had a major role of the magnetic field. The Earth's magnetic field has played a major role, and this is another example. So for example, when you see an auroral form that has like these curtains or rays, you are actually seeing the Earth's magnetic field, right? Normally the magnetic field's invisible. Can't see it. But the aurora effectively lights up some of these field lines so that you can see the structure of the Earth's magnetic field. Quite remarkable. And that also tells you that the magnetic field is playing some kind of very important role in terms of causing the aurora. But let's talk about what radio waves you get from the aurora. These are from like those antennas I showed you in the second slide that we put out, my research group puts out. And here's some of the kinds of things you can observe. If you put an antenna out under the aurora, and this is frequency on this axis again, this is one of these sonograms. Time, in this case it's about an hour across this graph, so it's a bit longer time frame than we've been dealing with. And it's also, check out the frequencies, much higher frequencies. I think this was referred to a minute ago. So this is thousands of kilohertz here, not kilohertz, okay? But let me point out there are three types of signals in here that we see. One of them is down here at the low frequency end, kind of up to a megahertz in frequency. This is called auroral hiss. All of our radio signals have interesting names, right? Hiss and so forth. This kind right here, this very broadband kind, okay, that is correlated with the hiss. You can see it's very closely correlated with the hiss. This is called the burst emission. And then you have this narrower band emission that's happening just near 3,000 kilohertz, right around 3,000 kilohertz. This is called auroral roar. And these are the three basic kinds of emissions that if you put a receiver out and an antenna on the ground underneath the aurora, these are the three types of radiation you normally see, radio signals you normally pick up. By the way, you see a lot of other signals on here that are of interest. I mentioned earlier, horizontal lines are typically man-made signals, and you'll see a lot of those between 550 and 1600 kilohertz. That is your AM broadcast band. And so these are all AM broadcast signals right here. This is, by the way, is nighttime data. It says 6 o'clock, but that's 6 o'clock in London, England. Geophysicists always use the time in London, England. So this is midnight, in Alaska or something like that. So it's in darkness, and in darkness, the AM radio signals, they propagate long distances subionospherically by bouncing off the ionosphere, and that's why you're picking up all these radio stations. There aren't that many in this station. This is in northern Canada along Hudson's Bay. There aren't that many stations. You can see that, by the way, in the middle here, all those stations fade away at about this time. That's because the aurora suddenly became very activated at that time. This is a typical signal of the aurora being very activated. It essentially turns off all of these distantly propagating radio stations. It disrupts the propagation, the subionospheric propagation of these stations. All of a sudden, you don't see anything except the local ones, right? This station right here must be the local station from this small community. The other ones that had to bounce off the ionosphere are getting absorbed because of the action of the aurora. And that same auroral action is causing all these emissions. It's interesting radio emissions. But anyway, one thing you can see about this is that with these ones, you can't just play them through a loudspeaker, okay? Because this is like way higher than any human can hear, right? Humans can hear up to a few kilohertz, or maybe you guys can hear a lot higher than I can. But anyway, even you guys can't hear hundreds of kilohertz. So you've got to do a couple of processing tricks if you want to listen to these things. And the first processing trick that often is done is that you do what's called down conversion. You'll take a small audio band snippet of these things, convert it down to baseband, and then you can listen to it audibly. So here's an example of that. So here's a rather unspectacular roar emission up here. This little blip lasts about a minute or so. But what we do is we take this thing, shift it down to baseband, and here's what it looks like. This is a 10 kilohertz bandwidth, so this we can listen to. And you can see that you wouldn't guess from that plot, but it's highly structured. Let's hear what it sounds like. Hopefully it'll play for us here, if we can get it to. About 45 seconds here, so you have to be patient. We're in this quiet part. Now we're good. You can hear a bunch of bizarre, generally rising tones in this case, right? So again, this is nature making these noises that we're getting to hear. Let me play a few other examples for you. These are just short snippets, but they show you the variety of signals. It's not always just rising tones like that. Whoops, wrong thing here. Let me go back. Let me see if I can get, we want to play each of these. So there's an example of just a whole bunch of short bursts. This one is more like the one, whoops. This one is more like the one we heard before. Rising tones. This one, which sounds more boring than it looks like it should, this has, notice, kind of almost sinusoidally varying tones. And down here, I think we just have a bunch of streaky monochromatic things. There's quite a variety of kinds of sounds you can hear coming from this auroral roar emission. Roar is kind of a misnomer. It doesn't really sound much like a roar. By the way, the thing that keeps coming up here, if you want to hear more of these, you can watch the movie Solar Max. This is an IMAX film that came out about the sun. It's worth watching if you get a chance to see it. But in this film, when they show the aurora, there are some sounds in the background. That's our sounds. It's a roar. And we're like in the credits. You can't blink, but you'll see us in the credits. But anyway, it's a fun one to watch. Let's talk about the MF burst. So the MF burst is the other emission that's much broader band, right? In this case, it's like not just concentrated at 3 megahertz, but it's usually at least 500 kilohertz wide. So for this emission, there's a different strategy for sonifying it. So what you do is instead of like down converting, instead of taking a small snippet of it and down converting like a 10 kilohertz bandwidth in order to listen to it, what you do is you basically slow down the whole recording so that basically instead of being 0 to 4 megahertz, it's 0 to 4 kilohertz. Basically, you play it back very, very slow. But then if you were to slow this down by a factor of 1,000, we'd be here like until 8 p.m. or something listening to it. So you have to do some tricky signal processing to chop it up when you replay it so it doesn't take so long. But anyway, here's your MF burst emission. It looks, it was called MF burst because it looks kind of bursty on a coarse time scale. When it was first discovered, actually our group discovered it, and we gave it that name because it looks like just bursts. But it turns out that when you blow it up, and this bottom plot shows a blow up of just 4 seconds or so, you can see it's not really a burst at all. It has a whole bunch of small structures, predominantly downward going, but a whole bunch of small kinds of structures to it. It's not featureless at all. It's quite complex. Let's play it here. And interestingly, this one, even though the roar sounded kind of like bursts, the burst sounds more like a roar. Let's listen to it. Whoops, wrong thing here. Let's go up here.
You're playing that, it's just down converting the frequency, not like AM divided by
No. All we're doing here is essentially slowing down. Essentially slowing down so that 4 megahertz becomes 4 kilohertz. We're playing this interval here, and it's stretched out. You'll hear these noisy bits. Hear that? Unfortunately, there's a bit of a background. I think you can hear the signal on top of that. We're almost done. So anyway, that is the MF burst. Sounds more like a roar. And that's the other strategy for sonifying. One strategy is you down convert an audio band, zip, and listen to it. The other strategy is to play the whole thing really slow so that you map the whole thing to an audio band. Yes?
I'm confused, so when I don't understand, so what is the difference in extracting this signal or processing it? What do you-
Oh, this signal, the way we did this signal was, the way we did the other signal was we essentially selected an audio band, 10 kilohertz, and we down converted that to baseband. And the way you do that is you beat it with a signal with an, yep, that's right. You're literally shifting the frequency, and then you filter it, and you have a 10 kilohertz that corresponds to a 10 kilohertz band of this thing.
So when you
This.
say filter, so you're extracting the part from DC to 10 kilohertz.
That's right. That's right. And you're taking basically a 10 kilohertz snippet through there. That was the first method. That was the method we used with the roars. The other method is basically you take this whole thing, you play it back really, really slowly. So artificially slowly, so that 4 megahertz is 4 kilohertz. And then you can hear it. You kind of hear the whole thing. It's kind of a false image in a way, but it's a way of sonifying it. But of course, if you really slowed this thing by 1,000, it would be 4,000 seconds. We'd be here for an hour. But you have to do some tricks.
But you started at a particular time. So it's equivalent basically to tape recording it and then just slowing down the tape.
It's equivalent to that. It's equivalent to that, exactly. Okay, so let's see, how much time do we have? Are we doing okay? I guess we're doing okay time-wise. So, okay, I thought I'll say a few words about what causes the roars and bursts. But to do that, we have to understand what causes the aurora. So let me say a few words about that. So the aurora is also, the solar wind and magnetic field play a key role. And so the idea is the Earth's magnetic field, if the solar wind weren't there, the Earth's magnetic field would look like this. It would be the field of a bar magnet. What the solar wind does is it compresses the magnetic field on the one side, and it stretches the magnetic field out into what we call a tail, a magnetotail on the other side. And how does the solar wind do this? It does this by driving electrical currents, right? Because if you think about it, the source of magnetic field, if you've had first-year physics, the source of magnetic field is electrical currents. And so you can kind of think about it. What magnetic field do you have to add to this to get that? Okay, that magnetic field has to be produced there have to be currents that produce, electrical currents driven that produce that magnetic field. And those currents are quite complicated. You can ask a physicist to tell you what they have to be, okay? Here's a picture of these currents that are essentially driven by the solar wind. The red are some of the currents. This is, again, a picture of the Earth in the middle. This is what we call the magnetosphere. It's the region dominated by the Earth's magnetic field. And the red shows some of the currents that are driven by the solar wind. The most fundamental one is this magnetopause current that literally is caused by the fact that the charged particles impinging are, the electrons go one way and the ions go the other way, and so you get a current. But you drive all these other currents in the system. And the interesting thing about these currents is, of course, currents, they never go in a linear fashion, right? They pick the path of least resistance, which in the case of the magnetospheric and ionospheric system has many of these currents diverted way down into the ionosphere, okay? Because that's the least fastest way. It's better for the current to flow all the way down because the magnetic field lines are like wires. The charged particles can move readily along the magnetic field, but not so well across. And so many of these currents, basically the current, when the solar wind drives the current, the natural path, instead of being a direct path, is for the currents to go in along the magnetic field where there's very little resistance, cut across in the ionosphere where you have a lot of charged particles to carry the current, and then back out. So you get these so-called field-aligned currents driven. And the interesting thing is that they tend to be driven right into this little ring. I don't know if you can see it there, right into this little ring. And that's exactly where the aurora is happening. Here's an image from a satellite, an ultraviolet light of the aurora. You can see the aurora is like a little crown on the Earth. It's happening right at this little place right here where these field-aligned currents are being driven into and out of the Earth's ionosphere, right at those points. That's where the aurora is happening. And the ultimate driver is the solar wind. So when the solar wind is particularly strong, there are other factors, but when the solar wind is very strong, it will cause that ring to expand. We might see the aurora here. Hard to see in Boston, I'm afraid. But if you come up to Hanover, New Hampshire, you can see it more often. We see an aurora maybe a few days a year in Hanover. And those are days when the solar wind is particularly strong and intense. It's driving all these currents, so it drives the show, essentially, for the aurora. But here's the details. I like to refer to the aurora as nature's TV, right? Although this is an old-fashioned TV, right? Modern TVs don't work this way anymore. But the way TVs used to work was you have an electron gun in back of the TV screen, and it fires an electron beam. And basically you raster that electron beam across the screen. When the electrons hit the screen, the screen fluoresces and gives off light. And if you raster that beam across the screen faster than the eye can follow, you make the images of your television. And so the aurora works very similarly. It's nature's TV. Instead of the screen, we have the atmosphere. And basically the current that's being driven by the solar wind, this current is being forced into and out of the atmosphere by the solar wind. And this current has to be carried by charged particles, and specifically by electrons primarily, because they're the more mobile species, so they carry the current. So the active region is actually in the upward current, where the electrons are coming down, carrying that current. And these electrons have to be accelerated considerably in order to carry that current, because there aren't very many electrons up here. And so you get a natural acceleration process, just like this electron gun in back of the TV. It's at maybe 5,000 kilometers altitude. You get this natural accelerator that accelerates the electrons downward into the atmosphere. And the atmosphere is like the TV screen. And you see these beautiful images. That's your aurora. It's nature's TV is what we like to call it. And the radio emissions, the roar, the hiss, and the burst are also coming from this region down here. And what's going on here is you have an electron beam. So it's kind of like the opposite of the chorus in a way. You have a situation where you have an excess of parallel electron velocity rather than perpendicular. But in any case, it's an unstable situation, and nature tries to correct that. And one way is through resonant wave excitation. So by the way, there's the aurora that you get down low underneath this natural accelerator. But anyway, let's talk about the other fundamental resonance in a charged particle gas, right? We talked about one resonance is the cyclotron frequency, the frequency at which an electron will circle around the magnetic field. The other resonance is called the plasma frequency. And the way to look at this is, suppose you take your charged particle gas, and suppose you shift the electrons off of the ions, like this. You imagine, what are those electrons going to want to do? Okay? They want to get back with their friends. They're going to feel a push to the left to bring them back to the right. Opposites attract. So those electrons are going to shift back like that, but now they're in motion. They're going to overshoot. And now they're going to feel the force that way. Whoops. Let me go back here. They're going to, whoops. I think I have the whole thing here if I can do it. So let's see, over that way, over that way, over that way. Whoops. That's this. I have to go back like this. And this is called the plasma frequency, It's one of the fundamental resonant frequencies in a plasma. And the other one being the cyclotron frequency on the left here, which we already talked about. And whereas the cyclotron frequency is proportional to the magnetic field, the frequency of oscillation of the electrons around the ions, that's related to the electron density. It's actually proportional to the square root of the electron density. So it depends on how many particles per cubic centimeter you have. Tells you what that frequency is going to be. And so it turns out the MF burst, for example, comes from this plasma resonance. It's a little hard to, here's a bit of an abstract plot here. There's a plot of frequency on this axis, altitude on this axis. So we're talking about a few hundred kilometers above the Earth is where these things are coming from. And what's plotted here is the cyclotron frequency, right? This is the frequency of the cyclotron resonance. And that goes down with altitude because the magnetic field becomes weaker as you go up away from the surface of the Earth, okay? And this is twice the cyclotron and 3 times the cyclotron frequency. The other frequencies that are shown here, these are the plasma frequency resonance, the one I just told you about. And they depend on the electron density. So they have the biggest frequency where the electron density is highest, which is in this layer that's called the ionosphere. The ionosphere is a layer of charged particles, right, at about 350, 400 kilometers. This is a layer of charged particles that reflects your AM radio waves. And so there you have a large density of charged particles. That's where the plasma frequency has its highest value. And so you have the plasma frequency goes down here and down here. And current thoughts about the medium frequency burst is that it is excited by this electron beam coming down, and it's excited at the plasma resonance. It's a resonance when the plasma frequency matches to the radio frequency. You get, again, this resonance that allows you to extract energy from the particles and put it out as radio waves. That's what's thought to be the MF bursts, not for sure, but thought to be. And it's sort of thought that the structure, the frequency structure, has to do with bursts of electrons coming down and giving, different frequencies at different times, and also dispersion properties of the waves once they're generated. The roar is very interesting because it's of course at a specific frequency near 3 megahertz, and it's thought to be at what's called the double resonance. There's a very special points here where a harmonic of the cyclotron frequency matches to the plasma frequency. And you get both resonances happening, right, at the same frequency. And that's the condition to get those roars. That's why they happen fairly narrowly around 3 megahertz, because that happens to be the frequency that's close to where twice the cyclotron frequency matches to the plasma frequency. Double resonance. But the interesting thing you might ask is, okay, this is the basic generation mechanism and why we get those radio waves, but why do they have these peculiar structures? Well, in the case of the roar, the structures are thought to arise because of density structure that's in the aurora. The aurora is a very disturbed region because you have these electrons pouring down into this region and generating ionization. And so you get all this spatial variation in the ionization. And the spatial variation tends to be aligned along the magnetic field. And so what you get is these waves, the roar waves that get excited, they can get trapped in this density structure. And if you have a condition where the density structure, the dimension of the density structure is comparable to the wavelength of the excited radio wave, then what happens is you get standing waves forming in this structure, and the frequency of the waves is discretized. It's very similar. It's analogous. This tries to show it here. This shows a column of density enhancement, and inside that, the wave field gets discretized because standing waves are formed, essentially. But the analogy you might draw is to a drum head. Right? So it's very similar to the physics of a drum head. In the drum head, the motions of the drum head are not arbitrary because the drum is fixed, right? The head is fixed at the edges. And so when you hit the drum head, it's going to be a combination of some kinds of modes, discrete modes, that have to do with certain numbers of waves fitting around the drum head. This shows some pictures of these modes. And so this is a close analogy to what's causing the structure in the auroral roar. Only instead of a drum head, it's a density enhancement, and the waves are trapped in there, but they're kind of making standing waves the same way that standing waves are made on a drum head. And so you get, instead of getting just an arbitrary frequency distribution, you get certain discrete frequencies corresponding to the waves that fit on the drum head. And so here's a picture, here's the basic idea. The idea is you have your roars, they're excited at this double resonance, where both resonances happen at the same place, but the density is irregular. So in the density, you get standing waves forming, and you get discrete waves, not continuous, but discrete. And then those discrete waves are preserved in the radio emission. And that's why you see all these little discrete multiplets of features. And the frequency change is thought to be because these variations in the dimensions of these structures that are trapping the waves. They're kind of unstable because they're being formed by ionization that changes with time, and so these things are constantly changing shape and so forth, and that's giving rise to, to variations in the frequencies. This is the thought, anyway, about what causes the structure of these waves. Let's see. We have just a few moments here. Let me finish by just showing you I'm going to show you one final wave emission because it's so important. It's called the auroral kilometric radiation. It's observed with satellites. So here we can give it a listen. Notice the frequency is in the tens of kilohertz. We can't hear it, but the slow down technique has been used. The tape has been run slow so we can shift this into the audio. Whoops. Let me go back to it and play it for you. So this is called auroral kilometric radiation. It's
May 10th, 1996, at 38 AKR.
AKR, auroral kilometric radiation. There's a fourth type of auroral radio signal. Which gives rise, you can hear it. This is one type of sonification where you take the whole emission and sonify it by just playing it slowly.
University of Iowa's polar plasma wave instrument.
The other sonification is where you take a snippet, and this is the other sonification method. You take a few kilohertz snippet of the AKR, and you down convert that. So let's listen to what it sounds like on this type of sonification. So you can see that the AKR on a broad scale, these structures are very fine. You didn't notice them when we played the broad scale. You probably didn't hear these kind of structures that you hear when we look at a very small piece of the AKR. But let me finish up by just, the main reason I mentioned the AKR is that it is by far the most intense radio emission from Earth, okay? The AKR originates not near the ionosphere, but it originates where the electrons are being accelerated, in this region where the electrons are being accelerated. That's where the AKR comes from. And it's beamed out into space, and it's extremely intense. About 1% of the energy of the aurora goes off in radio waves. And that's something like a gigawatt. It's an extremely intense radiation coming from Earth. The Earth is just a blaring radio source out in space. The interesting thing is we didn't know this until the 1970s. AKR was not discovered until 1974. And the reason was that it's beamed out. The source is at 5,000 kilometers above in the aurora, where the acceleration is happening, and it's beamed away from the Earth. So if you're on the Earth, you can't tell that you're a radio source. You have to put a satellite out in space looking back at the Earth, and it wasn't until the 1970s that a suitably instrumented satellite was put out there, Don Gurnett, University of Iowa, and they discovered that the Earth was this blaring radio source. It was known long before that Jupiter was a radio source. That's because we get to look at Jupiter. We can see it, the radio waves coming from Jupiter. But our own planet, we had to wait 20 years longer to learn it was a radio source. That's a very interesting question. There are two issues. I don't know of any, I don't think that's, you'd think in principle you could, but I don't know that anyone, I've not seen any paper reporting that. That's an interesting idea, whether one could look for that. But I know of no papers that have ever, no one that has ever observed such a thing. So it's a huge, powerful radio wave going out. And the one thing I wanted to mention is that it turns out that it doesn't just go out, though. That isn't quite correct. And so there's recently evidence has come up, and our group's played a role in this. The top panel shows auroral kilometric radiation observed by a Japanese satellite 100,000 kilometers away from Earth. So this is the AKR streaming out away from the Earth. The bottom panel is observations at South Pole on the ground. And there's some commonality between these. And we suspect that some of that AKR is leaking back. This isn't reflected off the moon, but this is actually leaking back. So the idea is the radio source is here. Almost all the energy goes out into space, but some small amount leaks back and can be observed on the ground. This is a tough one for amateurs to measure, though, because you can't see this at Northern Hemisphere. You have to get away from civilization. The problem is the AKR happens in a band that's has a lot of interference in it. So that's why you have to go to Antarctica to measure the AKR on the ground. What stops it what normally does for the escaping stuff? There are two things. First of all, it's beamed. First of all, it turns out the source is in a density cavity. It turns out that where these electrons are accelerated, because they're accelerated, there's a kind of evacuation of electrons. So there's kind of a cavity there. And then they're accelerated, the waves are generated perpendicular to the magnetic field, but they are refracted outward. They're refracted outward because of this density cavity structure. And so they're refracted away from the Earth. And furthermore, even if they came toward the Earth, the frequency is below the critical frequency of the ionosphere. So in principle, they shouldn't be able to get through, even if they came toward the Earth. So that's why the bulk of it goes away from the Earth. And for decades, the assumption was you have to be in outer space to see the stuff. But I think we've shown that's not necessarily true. It's possible to sneak some of the energy into a different radio mode called the Whistler mode, because it's the same mode that the whistlers propagate in. And it can come down the field line and actually get to the ground. But a very small fraction of the power. But nonetheless, kind of a diagnostic of sorts. I'm not aware of anyone observing anything coming off the moon. That's an interesting idea. Or off of other structures or something. It may be the moon is not that conductive. It may be, yeah, it may be the moon's not an ideal. So let me just finish by just showing you this picture of all these. This is a picture. I've modified it a little. It shows some of the wave phenomena. We've only talked about a handful of these, okay, right? So I talked about the whistlers, which are here, chorus, burst and roar, AKR, but you can see there's a whole lot of other ones, okay? We could be here for hours talking about all these different radio emissions. And you can see that this is something that can keep someone busy for a career, okay? And I'm looking at all the young people here as something to consider. It's very interesting. Not only can you study all these interesting phenomena, but you can get paid for it. And that's because this system has significant impacts on our technologies, right? So the Van Allen belts that I mentioned are a danger to satellites. They've been known to kill satellites. They undoubtedly will kill satellites in the future. Satellite communications, including GPS, can be significantly affected by these phenomena. GPS is very important for our everything these days. Power systems can be brought down by induced currents from the current systems that I described. Has happened in the past, will undoubtedly happen in the future. Because of these and other impacts, there's a high interest in understanding these things and studying them. So you could have a career investigating all these interesting wave phenomena. The other thing is, if you're an observer, an experimentalist, you get to combine your interest in the Earth environment with traveling to the ends of the Earth, right? Because you have to go where the physics is. That's the motto in our field. And so you end up going to the Arctic, the Antarctic, the equator, everywhere you want to go. So anyway, I would give a plug for the young people here to think about, space physics as a career. Rich subject, has an impact on society, is important to study, and it's a way to combine academic career in physics with adventure. So I'll finish with that. Thanks very much. Yes.
Interference from other sources. There's other sources in the 1.5 to 3 megahertz region.
Yes.
Yeah.
Yes.
And there are also, even at the 10 kilohertz region, there are radio emissions.
There
faster
are.
radio emissions. So
Absolutely.
Is that part of the reason why you really want to go to, the North Pole or the Antarctic
or the Antarctic?
Get as far away as at least from.
Absolutely. Interference is
Proximate sources.
a serious problem, particularly at the range of these bursts and roars, as you mentioned, the megahertz type frequencies. Interference is a huge problem. And that is one of the things that drives us to take our instruments to Antarctica, because you can get thousands of kilometers away from the nearest radio station. Unfortunately, the Antarctic stations themselves have not been very good about keeping electromagnetically clean. So we still have problems even in Antarctica. But that drives us. We do a lot of our experiments in Antarctica. Of course, we do our experiments in the high latitudes, the Arctic, just because we need to be near the aurora. So that drives us high latitudes. But unfortunately, the northern hemisphere high latitudes are still very replete with interference. You're not far enough away. And so there are some phenomena you can see there, but others you have to go to the Antarctic. I don't know if that addresses your question. It's a serious problem. Interference.
Well, it goes back to my initial question: is how strong are these emissions? I mean, what kind of signal strength are you talking about?
Well, typically like tens to hundreds of microvolts per meter at ground level. Something like that is the typical signal, like for these bursts and roars. Strong ones might be 100 microvolts per meter electric field. So reasonably loud.
But all of our, LEDs and things are populating that space at much higher levels in general.
Yeah, no, it's true. Yeah. Interference is a real problem for us. And I will say that the roar and burst signals are not a whole lot of power. Turns out to get that kind of signal strength from a few hundred kilometers away, you only need a few watts source. So those things are typically, unlike the AKR, kilometric radiation, that's a hugely, by the way, the gigawatt figure is for integrated over the whole Earth, not an individual source. But anyway, those are much stronger. Yep, that's right. And that's during a particularly active time, too. That's probably kind of an upper bound. Yes?
Is all of this controlled basically by the charges coming out of the solar wind? I mean, is it just all dependent on how whether strong or weak? That's what turns.
That's a major driver. Most of the phenomena I've talked about are essentially driven by that. The exception is the lightning, which has nothing to do with the solar wind. But a lot of these other phenomena, the solar wind is playing a huge role in driving the show. And it's complicated because it's not just the strength of the solar wind. It turns out the direction of the magnetic field, the solar magnetic field, has a lot to do with whether the solar wind is effective or not at pushing on the Earth and driving the circulation. So it's not a simple problem, which is why people have been working on it for 30, 40, 50 years and still haven't really cracked it. We still can't predict the weather in outer space as well as we can predict the weather here. That's a goal of our field, is to be able to do that.
So I'm going to make two sort of comments relative to this comment about trying to hear these signals in the presence of other things. I'm going to refer to the upcoming lecture in this series. Alan Rogers is going to talk about detecting even fainter things from the early universe where interference is a major problem. He's not at these frequencies. He's up at sort of VHF, FM. But listen for that forward reference when you think about figuring out what's not the signal you want versus the signal you want. And for the students in the room, you don't only get to do this from the ground. Now when you have small sats and CubeSats, you can also do that affordably from low Earth orbit. And there's a lot of student teams, including one that Jim is involved with, and Mary over here and myself, who are trying to put radio receivers in low Earth orbit on a small platform to try to pick this stuff up from low Earth orbit above the ionosphere, where some of these cutoffs that Jim was talking about don't occur. So you can actually study this a little closer to the source. So there's cool things to do involving that.
We're going to be hiring summer UROPs. Keep your eyes open.
All right, that's great. That's great. Absolutely true.
Hypothetically, where would you have to be to hear the radio waves from the sun? Because the sun has a magnetic field, right?
Yep, the sun emits a whole zoo of radio waves. That's a fascinating topic, and I'd recommend you invite a speaker to talk about that. It's really interesting, type 1, type 2, type 3, type 4, type 4A, type 3B, there are a zillion types. And they're all very interesting because they give diagnostic information about what's happening in the solar wind. Some of them you can hear from the surface of the Earth if their frequency is above the cutoff frequency, which is typically 1 to 10 megahertz. So, for example, the solar type 3 emissions extend up to hundreds of megahertz, and you can see the high end of those quite easily from the surface of the Earth. Many of the other ones you do have to be on a satellite to see. But it's a fascinating topic. And by the way, some of the mechanisms for those are the same as some of the mechanisms I've talked about. One of the motivations we have for studying the roar and burst is that it's a close-at-hand laboratory for studying the same emission mechanism, physics, that happens in the solar wind or at other planets or even stars.
Does the Earth or atmosphere have an overall negative charge because of the electron leak?
That's a very interesting, very good question. So the charge of the Earth and of the ionosphere is not really determined by the things I've talked about here. So there actually is a global electric circuit that controls kind of the charge of the ionosphere and the Earth, and it's primarily driven by thunderstorms, it turns out. And so it's basically tropospheric phenomena that essentially determine that, okay? These phenomena I'm talking about have relatively little influence on that. It's a fascinating topic again, and I recommend inviting a speaker on that topic. Actually, the grandfather of that whole field is a person named Ralph Markson, who was an MIT prof. I don't know if he's still alive or not, but he was the one who first described this global electric circuit whereby thunderstorms are constantly basically driving charge from the Earth to the ionosphere and controlling essentially the relative charge, the fair weather, what we call the fair weather electric field. There's a relative potential difference between the ionosphere and the Earth, and it's maintained by the thunderstorms. And you have one sign of fair weather electric field and a different sign in the thunderstorms that are charging it up. Fascinating subject. But this has relatively little to do with it.
Jim, you can also mention there's a guy named Earl Williams.
Oh, good point.
Because it turns out that between the surface of the Earth and the bottom of the ionosphere, you can think of it as a resonant cavity. And so some of the thunderstorms can excite very, very low frequency waves. Now we're talking about 8 hertz. 8 hertz. Below the cutoff of the subwoofers in your speaker system at home. And they actually roll around the planet. In fact, if you want to count the number of lightning strokes from the planet, you put up a receiver for those very low frequencies, and it doesn't matter where you are, you're going to see all the lightning strokes everywhere. You can actually count them.
Yeah, this stuff is fascinating. Earl Williams would be a good person to invite for your seminar series. Yep. Yes.
So back to your first topic of the whistlers that bounce back and forth along magnetic field lines. How perfectly do those hold to a single line going back and forth? So like lightning in Idaho, could that bounce off South America and then we hear it here in Boston?
Well, that's a very good question. First of all, it turns out that in order for them to make this trip, the magnetic field is not sufficient to guide them by itself. So they require actually a density structure that's aligned along the field. It's called a duct. And so a duct has to be present in order for them to make this trip. So there's some other physical process going on that forms these ducts. As I mentioned, transport of charged particles is rapid along the magnetic field and slow across the magnetic field. So it's fairly natural for field-aligned density structure to form in the space environment. But you require such structure in order to get whistlers. If it were just the magnetic field and a uniform environment, the whistlers would not be sufficiently trained along the field to make the trip. So you need these ducts to be present. There usually are ducts out there, but they're in different locations. Now, this is where subionospheric propagation comes into play. A given lightning flash will illuminate a fairly large region, many hundreds of kilometers in radius. And so any ducts that are present in that region will get excited and transmit energy to the other side. When the energy exits the other side, it can also propagate hundreds of kilometers. So you can observe, if you are within several hundred kilometers of a duct, you can observe energy coming out of that duct, whistlers coming out of that duct, that could have been excited by a lightning that could be several hundred kilometers away from the other end of the duct. All of this has been pretty nicely measured by this point, because these have been known about since the 50s and so forth. So there's been a lot of very detailed measurements of these ducts and the properties of the whistlers exiting the ducts, this kind of stuff. Fair number of papers that you could look at. So, yep, I don't know if that answered most of your question. Okay. Any other questions, or is it time to have the pizza or something? The cyclotron resonance. The basic idea is that the electron is going around the magnetic field in a circle, And this is perpendicular motion, right? The motion of the electron is perpendicular to the magnetic field because it's going around. And the idea is if the radio wave, which we're envisioning here as a transverse radio wave, that its electric field is also perpendicular to the magnetic field. So, so the idea is that if the electric field of the wave switches at the same rate that the electron switches directions as it goes around, then you have the possibility for the field to constantly push the electron in the direction that it's going, right? So if the idea is if the field is in such a way that it's pushing the electron, if the field switches direction at the same time the electron changes direction, the field will continue to push the electron, and then again continue to push the electron. So the electron can be accelerated out in a spiral pattern to a much larger radius and a much faster speed. And the reverse can happen, of course. The electron can be decelerated by this process. So this is called cyclotron resonance, and it's the physical process that's responsible for amplifying the chorus waves that we talked about. But it plays a big role also in the AKR, which I didn't get into, but AKR is cyclotron resonance is critical for that as well. And it's one of the fundamental resonances in a charged particle, a magnetized charged particle gas. The plasma physics is a fascinating subject. And the charged particle gas, I always like to say that everything in a neutral gas, you have sound waves. In a charged particle gas, you also have sound waves, but you have a whole zoo of other types of waves that don't happen in a neutral gas that are mediated by electric fields and magnetic fields and so forth. So it makes for a really rich topic, really interesting and rich topic of different kinds of waves that you see playing out here in this environment. So a fascinating area of physics to study, and still lots to be learned. So anyway.
Another question, this has to do with the solar system, but when these Voyagers go out, at least Voyager 1, Massachusetts across the border, leaving the solar system.
That's right.
The purpose of well-defined boundary is not just taking some arbitrary percentage of something. And I mean, there's physics close to this at least. Can you explain what makes that a boundary?
Let's see, I think we're talking about, there are a couple of boundaries out there. There's something called the heliopause, and then there's also a shock structure that stands in front of that. And I'm trying to remember which one Voyager is crossed. I'm looking over at Phil.
You can also think about, a magnetic field has a given tension to it, right? So you can actually, the magnetic field sort of has a pressure, if you want to think about it. You think about a particle which has kinetic energy. As it's going in, if it's charged, the magnetic field is more and more stiff to the motion of that charge. So in some sense, you can think of the magnetic field having equivalent magnetic pressure that's pushing back on the charged particle, because the charged particle cares where the magnetic field is.
And this allows a shock wave to form in front. But the heliopause is basically the boundary between the sun's magnetic field and the magnetic field that comes from somewhere else. So it is a sharp boundary. It's a very pronounced boundary because you're leaving magnetic field lines that originate on our sun, and you're going to magnetic field lines that originate somewhere else. So in principle, it's a very sharp boundary. And so I think that the problem is, of course, there's a lot of structure out there, and so there was a lot of argumentation about when the satellite actually crossed that boundary. And then there's this other boundary in front, which is the shock wave, which I think we were getting at here. The fact that charged particles are affected by this magnetic field boundary causes them to kind of be backed up. There's like a back pressure that causes a shock wave to stand off in front. And so I'm not sure whether the Voyagers have passed both the heliopause and the shock, or just the heliopause.
About whether they have or not, because the problem is that in any place where you have a sharp transition from one region to another, nature never wants to have a step function there. You get a lot of turbulence, which just like, the shock wave in front of a boat in a river. And so there's a whole lot of structure, and
it muddies the waters, let's say.
So
muddies the
it's
waters.
not like on-off. There's a transition period where you can trying to decide if you've gone through all of the shock structure, and now you're out into a different regime.
Wait, that shock wave is coming from what?
That's coming from the fact that
there's an interstellar wind, right?
Yes.
There's an interstellar wind. The material that's outside of the sun, that's associated with interstellar space, is moving. Now, our solar system is moving relative to that material. So that means there's a relative velocity of that stuff coming into our heliopause. And that velocity then causes a shock that stands off away from the heliopause. That's my understanding anyway.
Yeah, and this is also, of course, going to depend on how stiff that magnetic field is, if that's the thing that's providing the boundary. For example, if you replace that Earth planet there with Mercury, Mercury has a very weak magnetic field, which is reasonably disorganized compared to the very nice one that Earth has. And so the shock upstream of I meant Mars.
Mars, yep, Mars.
The solar wind almost penetrates right down to the surface. It's not where you get this magnetic structure standing thing off. Or if you think about Jupiter, Jupiter's magnetic field is
much stronger.
Puny by comparison with Jupiter. So the Jupiter magnetosphere is the largest object in the solar system, distance-wise. So that has a completely different structure with different organizations of plasma waves in it, which is a whole nother people's spacecraft room.
You can make a map like this for all the planets, right?
Yeah.
All these phenomena. That's why there's no shortage of stuff to study. Yes.
So I know in the 60s, before communication satellites became reliable, there were a lot of interesting attempts to communicate over the horizon, including like launching needles.
Needles,
into space.
yep,
Yeah.
the needles experiment.
Was there ever any effort to use these ducts to send messages over long distances, to your knowledge?
Not that I know of. Now remember, the VLF signals that are propagating in these ducts they're not very practical for information because they're so low frequency. That's one thing. But I don't know of any communication attempts. I do know there have been a lot of experiments called channel probes that probe the ionosphere by using, megahertz waves or something and looking for ducts. It's particularly true. There's a phenomenon called equatorial. There's a phenomenon that occurs above the equator, a turbulence phenomenon called equatorial spread F that creates density structures. And you can often observe waves ducted in those structures. So you can get anomalous propagation from the southern hemisphere to the northern hemisphere through those structures. It's very interesting. Yeah, this stuff is generally pretty well known because it has practical implications, and HF has been used for a long time, and so people kind of know about this stuff. But whether it's actually, I don't know if those kind of things are usually thought of thwarting communications, rather than being used for communications. So I don't know of anybody that's tried to use the ducts for communications. There is a very interesting proposed use of VLF waves. And that is to, there's talk about mitigating effects of artificial radiation belts that could be formed by exploding a high-altitude nuclear device. There's been a lot of concern that even a small nuclear nation could detonate a nuclear device at some altitude and essentially create a very strong radiation belt that would destroy, within a few months, would destroy all of our satellites. And the idea is that you can use these chorus-like or whistler-like waves, you can launch them, and you can cause this artificial radiation belt to go away very quickly. There are a lot of experiments being done on this. It's called radiation belt mitigation. And its idea is it's a kind of defensive weapon against this possibility that someone could destroy our technology by deploying a nuclear weapon that way. So that's an example of a technology using kind of Whistler-type waves, but it's not communication.
Yep.
But it's a lot of very interesting things like the needles. A lot of interesting stories in ionospheric and space physics. Maybe everybody's ready for the pizza. There might be some left.
Well, in that case, thank you all for coming, and thank you, Jim, for joining us.
Thank you. Thanks for inviting me.
Just before you all leave, of course, just a reminder, please fill out the attendance sheet, and also, Phil mentioned Dr. Alan Rogers is going to be here next week. He's probably one of the most incredible radio astronomy people you will ever meet. He's spent years studying signatures for epoch of reionization. He's had a hand in dozens of other major high-profile projects. It'll be fascinating. And after that, Wednesday night as well at 7, if Actually, I guess it's 7:30. We have amateur radio exams. They'll be held over in Building 1. All the details about all of this can be found on our website. Thank you.